Okay. So today we're going to do a little quick look at circuits.
Got it.
And there's a bunch of vocabulary at the top. Obviously, if we're finishing this by Friday, we're not going to have a quiz on this vocabulary. But if you're thinking that physics might be something that interests you, you might, over the holidays, take a look at this vocab, okay, and make sure that you've sort of got a general idea of it. Page 104. So an electrical circuit, the circuit is just the path that an electric current travels, okay? What does the word circuit kind of sound like? Circuit kind of sounds like a circle, maybe? Okay, it could sound kind of like a surface also, but it starts with circ. It sounds kind of like circle, and in order to have a circle, you need to have one end attached to the other end. Okay, so we are going to start by looking at a simple circuit. All right, and a simple circuit has three things. It has what we call a source, and a source is what gives the energy to the electrons. So the source gives the energy to the electrons. So what is one source of that energy? What is one thing that can give energy to electrons? Yes?
A battery.
A battery, okay? Or an electrical outlet. You want to give something some electrical energy, you can just plug it in. You also need a conductive path. What kinds of things are good conductors? Metals. So usually this is a metal wire. Now over here I've also got a conductive solution, but we haven't talked about that this year because we're running out of time, so it's okay. The last thing we need, unless we want to have a short circuit, and short circuits are no good, is we need a load. And a load is the word for something that uses up the electrical energy. Can you think of something that uses up electrical energy? Yes?
Light bulb.
Light bulb uses up electrical energy. If you have a motor and you plug it in, it uses up electrical energy. If you have a speaker, it uses up electrical energy. Your phone uses up electrical energy. So all of those things would be a load. So those are the three things you need. You need to give the electrons, you need to have a path for the electrons to flow, and you need something to use up the energy of the electrons. So here is a picture of the source. We have the conductive path. And the conductive path actually goes all the way up through the light bulb. All right, this is also the conductive path. And the light bulb is the load. Now, I don't know if you remember trying to light up that little light bulb after our last test. Okay. Basically, what you needed is you needed a wire to touch this metal part here. You needed a wire to touch the metal that's on the side of the light bulb because the conductive path goes up and it goes through the tungsten wire, and it goes down, and then it comes out. There's another little bit of metal at the bottom. So a full conductive path would have a wire touching the side of the battery and a wire touching the metal part. Now, if you don't have two wires, you would just touch that metal to the terminal of the battery itself. Okay, so you were lacking that second wire. The second wire just makes it more convenient. Okay. All right. Now, irritating to draw this, yes? That would take a lot of work. You could simplify it. And one of the things that we do to simplify it is we make it as rectangular as possible. So we want rectangles. All right, we've got our source, we've got our conductive path, and we've got our load. However, I still figure this seems like too much work for me to draw. I am not a good artist, and I'm lazy. Let's make it easier to draw these things. So what we're going to do is for our lamp or light bulb, also known as a lamp, sometimes you'll see it called a lamp or a light bulb, there's actually 4 choices that you can use. When I was in high school, we learned this one. Okay, but I feel like that one's like harder to draw, because in order to draw that one, you kind of have to go like this, and then you got to go like this, and do, and then you put a circle around it. Yeah. Whereas you could just draw like this, and then draw a circle, and then draw an X. That's super easy. Yes. Other options, you can go like this and just put a lump, and then draw a circle around it. Any of those will do. Pick the one that you like and just stick with one of them. Okay? No need to learn all of them. Pick one. Okay? Now, a cell is actually a name for a battery. Okay, but in physics, we call batteries cells. This is the physics word. Also in chemistry, physics chem word is cell. And instead of drawing this whole thing with a plus and a minus, we just draw plus and minus. The plus is the long one, the minus is the short one. I guess that kind of makes sense because positive is bigger than negative. Yeah? And then the wire is just a line. So if we wanted to draw this little guy here, you'll notice that our positive is on the right and our negative is on the left. So what we would do is we would draw a positive on the right and a negative on the left. That's our battery. And then we would draw lines, and we're going to make it a rectangle. As straight of lines as possible. And then our load, I'm going to use the easiest lamp, I think. That is a circuit. That is a simple little circuit diagram. You have a question? No, okay. Simple little circuit diagram, easy enough. Make it rectangular, use the symbols. Now, interestingly, we could take this thing and we could say, okay, here I have a positive on the top, I have a negative on the bottom, and I could draw it like this. Lamp. Yes? But I could also draw it. And it doesn't matter that this doesn't look like a rectangle at all. It doesn't actually matter what side you put the lamp on. Okay, you could put the lamp here. Does the wire care whether it was longer before the lamp or after the lamp? No. And you could even, if you wanted to, here's a fun one. You could even put the lamp here if you wanted to. It just doesn't matter where you put it. You could put it anywhere, right? You could even put it, let's see, where else could we put it? We could put it down on the bottom, right? Doesn't matter where you put that lamp as long as it is after the positive terminal and before the negative terminal, okay? If there is no complete path, so if we don't have a full rectangle, or a full circle, I guess, we say that we have an open circuit. And by open, what we mean is we've got a wire, but we've broken it open, okay? So if we look here, this is an open circuit. What happens with the light bulb in a broken circuit? The light bulb is off. It's not broken, it's off. But if we were to, say, add a little bit of wire in this little section here, then all of a sudden we have, what do you think we call it? If it's not an open circuit, it's called a closed circuit. And this is now on, because the electrons can flow. You imagine if there's electrons all the way around here, right? There's electrons everywhere. I don't want to draw them all because that's tiring. So I'm leaving lots of gaps in between them. But there would really be electron beside electron beside electron beside electron. If I have a little gap, can they jump the gap? No. So that's why it doesn't light up. We also call an open circuit an incomplete circuit. We can call a closed circuit a complete circuit because we have an incomplete rectangle and we have a complete rectangle. Now let's say we didn't want to have a little piece of wire that we kept having to add in there. We could use a switch instead. And this type of switch is called a knife switch. And I'm going to go grab one. I think I'm going to go grab one. It depends on if they're there or not. Nope, they're being used by another class right now. So here's how it works. Can you imagine that I am made of metal? Can you imagine I'm made of metal? Okay, and this is the circuit here. Yes? And this is the switch. Right? So what happens is the metal moves in between the other two pieces of metal and it makes a connection. So you can just lift it up and the connection's broken. You can put it down and the connection is closed, right? So here we have that little piece of metal. It is closed. So this is on, so the light bulb shines. All right. Or we can turn it off, and this is what it would look like when it's off. You see, we've taken the little piece of metal out. All right, so this is off. So if we remember, our light bulb symbols are these four here. Our cell, what is a cell? A cell is a battery. And we have symbols for switches. You'll see them drawn different ways. You can draw an open switch. You put two little dots on either end of the line. Okay, and then you can either have it open or you can have it touching. I find this one to be harder to draw, so I don't usually use this one. I usually use that one. That is open, and then just that is closed. To me, that is easier to draw. This one, to me, looks harder to draw. If you're good at artwork, you can definitely do the other one, though. Okay? So what we're going to do, I think, is we are going to draw this circuit here. So at the top, we have our positive terminal. At the bottom, we have our negative terminal. So the positive goes on the top and the negative goes on the bottom. Somewhere or other, oh, stop moving around with me. There we go. Somewhere or other, we're going to have our light bulb. I'm going to put it on the side over here. Okay. And down on the bottom, we have a closed switch. So I'm going to put a dot, and I'm going to put a dot. That shows me that I have a switch, and it is closed. Why will that thing not draw properly? Come on. There we go. The only difference for the next one is we would still have the positive on the top, the negative on the bottom. Is our switch would be open. Is this easy enough? Yeah? Okay, cool. Does it matter if we were to move the light bulb up here? Could we move the light bulb up there? Would that be okay? Yeah. Could we move the light bulb down here beside the switch? Yep. It would not matter. Okay? They would all mean the same thing. A couple of other ways you could draw the circuits. You could even take your battery and say, instead of putting my battery like this, I could actually move my battery and put it sideways instead, if I wanted to. That's usually a little trickier though, right? Because you have to actually imagine turning the battery, which is a little hard. But if you imagine, if you turned this half a turn to the right, that's what you would end up with. You don't have to be able to do that. You just need to recognize that it is the same thing, okay? But you don't have to be able to do that, where you're actually imagining the battery going. Okay. If a circuit contains more than one load, so in other words, more than one light bulb, for example, it can be connected in one of two different ways. We can have a single pathway, one path. And if the two light bulbs are in the one path, we call that series. They are in series. The two light bulbs are in series with one another. There is only one path for the electrons to flow through. If we have two paths, that's called a parallel circuit. And if you think about it, it's kind of like, because this bulb is parallel to that bulb. And it's going to make even more sense once we draw these two circuits. So let's draw the circuit on the left. I'm going to move over to the left a little bit so I leave room on the right for the right-hand one. Okay, so this one, we've got our positive here. We got our negative here. I've got a light bulb. and it's connected by a little wire to another light bulb. And if you're interested, if these were the same light bulbs, if this was a 6-volt battery, this would give out 3 volts of energy and this would give out 3 volts of energy. That is totally something that you are not required to know this year. Okay, but they basically, if these are identical light bulbs, they would drop half their energy in the first light bulb and half their energy in the second light bulb. If you're interested as to why that happens, come and talk to me about it. Okay, but we're not going to learn it because we don't have time. Okay? Now, this one over here, I think I'm going to draw it over here. We've got a positive and our negative, and then we have one path here. And we have our second path here. And you can see how it makes sense now that we call them parallel, because those two pathways are parallel to each other, yes? So 2 paths is parallel, 1 path is series. And interestingly, if this was a 6-volt battery, this one would use 6 volts and this one would use 6 volts. Because electrons with 6 volts go this way and they drop all their energy, and other electrons with 6 volts go that way and they drop all their energy. Whereas the electrons here, they have 6 volts, they drop half their energy, and then they drop the other half of their energy. Yeah? Whereas this one, the electrons that are already in this path have 6 volts, and they go whoop, right through, and they drop all their 6 volts. The electrons that are already in this path have 6 volts, and they drop all their 6 volts as they go through. And then they meet up back here. Okay? So it's kind of interesting. I'm so sad that we don't get to do more with this because I actually love series and parallel. They're very exciting. So if you're ever bored during flex time, come and have a chat with me. I'll geek out with you over series and parallel. I live to dream. I know no one will probably take me up on that, but maybe someone will someday. So there we are. Now, series is convenient. It's super easy. But let's imagine that we have one light bulb that is broken in a series circuit. And you can see here's our little light bulb here. This didn't come through very well, but there's a little, the wire goes all the way through the light bulb. And over here, the wire, it's broken. If it's broken, do we have a complete pathway? No. So what do we call this kind of a circuit? It's called an open circuit or an incomplete circuit. And it doesn't matter that the other light bulb is working. If one light bulb is broken, can electrons flow in that path? No, because there's a gap, right? It's like the switch is open, okay, except for it's a light bulb. So there's no light. No flow of electrons. So in a series circuit, if one bulb breaks, the circuit will be open and the unbroken light bulb will not work. However, and this is why parallel is good, they used to make Christmas lights back in the days when my parents were kids. Okay, not by the time I was a kid, but when my parents were kids, they used to make Christmas lights in a big series circuit. So you would have light bulb, light bulb, light bulb, light bulb, light bulb, light bulb, light bulb. If one of those bulbs burnt out, they would all go out, and you wouldn't know which one. So you would have to go around unscrewing all the light bulbs, trying them one by one in order to fix it. So it was crazy. So they stopped doing that, and they started, if you ever notice with Christmas lights, there's not just a single wire, there's like a bunch of wires sort of stuck together. And that's because they are attached together in parallel. Because even if this pathway is broken, this pathway is still closed. So if one bulb breaks in a parallel circuit, one branch of the circuit will be open and the other will be closed. And so the unbroken bulb will work. On. So that's what they have nowadays. So if one bulb burns out, you don't have to worry about the other ones. Now, there's a reason that when you were doing that little thing with the light bulb, I said, do not touch the wire from one end of the battery to the other end of the battery, because that is what we call a short circuit. Okay? So here's 3 types of circuits. We have a closed circuit where the electrons move, okay? And the electrons move this way. Why is this pen being so silly? There we go. They all move around like this in this case, a counterclockwise direction, because they are repelled by the negative and they are attracted to the positive. And they're repelled by the negative. So we have a closed circuit, light bulbs on. We have an open circuit, light bulbs off. Now, if I attach a wire from here to here, it bypasses the load. And here's the thing, and we have not done resistance, which we don't have time to do. But can you imagine that this is like, this pathway through the light bulb is tough for the electrons to get through. This is like climbing Mount Everest. Okay, electrons getting through that light bulb, there's all sorts of things in their way. Okay, that light bulb filament is very uncomfortable for electrons to make their way through. There's a lot of resistance. So they're bumping into things and they're crashing into things, and there's like, I cannot make it through, and it's very difficult. But electrons love to flow through wires, and there's nothing in their way. So can you imagine if you had a river that could go one of 2 ways, and in one path there was like a line of boulders and somebody built a dam, and like somebody, there was a beavers were building, things in that one. Or there's this other one over here that's just free and clear and open, big wide path. Where's the water going to go? Free clear path, yes? So that's what a short circuit is. It's like a free clear path. So this is like, a free clear path. So the electrons will avoid the light bulb because it's hard, and they'll go through the wire, which is free clear path, but they move very fast. And when they move fast, they create a lot of heat. And when they create heat, you can get a fire. And last year, in September, not this September, last September, I woke up and I found, and actually I didn't find out when I woke up. I woke up, I went downstairs, I had breakfast, I came back upstairs. I'm looking at myself in the mirror. I'm like, what is all this stuff on my mirror? Like black nonsense all over it. I'm like, what's going on? And then I look down and there's my outlet. And it is black. There's like this thing on it. It looks like this. All above the outlet. There's the outlet. So, and there was a melted plug for a hairdryer. So the plug was melted. So I assume, and the hairdryer was off. Hairdryer was off. Hairdryer. See, I'm an artist. Look at me go. Okay, that's a hairdryer. Okay. Hairdryer was off. Somehow or other, there was a short circuit there. Yeah. And I don't know how it happened. I do have a window like over here and it was open and it had rained that night. So maybe some water got in. I don't think so. But I would recommend that if you have anything that is like a big heating, requires a lot of electricity, I would unplug it. So unplug your hairdryer when you're done. Even just turning it off apparently was not good enough. Could have burned to death in my sleep. I never woke up. The whole thing, like it just happened. Didn't even know it had happened in the morning. So just be careful with your electrical stuff. So I assume there was a short circuit there and that's what caused that to happen. And that's why I had this black nonsense on my wall. Okay. And that's all we're going to do for today. With the last few minutes, you can continue working on pages 80 to 81. If you are done pages 80 to 81 and you would like a little something to work on, you could try some of page 113, but that's optional, okay? 113, 114 is optional. If you're done in your board, though, that will work. Excellent. I will check you off. Thank you so much.
You're welcome.
Excellent. Wonderful.
Yep.